Hey class, Mr. Muhyiddin here with a video on a new topic, and that's dealing with horizontal and vertical tangents. We've seen them graphically. The main thrust of today's video is to understand how to determine and understand them algebraically or analytically. So it tends to help to do a bit of review with a graph, because most of us can at least get the gist of it through a visual. So here you'll notice this graph is mostly continuous, except for this point right here, which tells you right away that it's not going to be differentiable. But as you know, continuity does not imply differentiability, because you also have a non-differentiable point right here, thanks to the vertical tangent. So we're not only talking about vertical tangents, we're also talking about horizontal tangents. So we also saw in our early study of derivatives that a function's slope is equal to 0, and thus the tangent line there is a horizontal tangent line when the slope is equal to 0, and that typically happens when you have peaks and valleys. So we have a peak and a horizontal tangent and a valley there. So several weeks ago we graphed using the computers, or estimated the graph, or matched the graph of a function and its derivative. So here, one strategy for that is you'll notice that there is a slope of 0 there, so I know I'm going to have a y-x-intercept for my derivative graph here in yellow. And before there I have a positive slope, after I have a negative slope, so it's going to look something like this. Negative slope, because they're all downhill. More negative. Oops. Now this is interesting because there's no tangent line there, because I cannot be tangent to the graph because there's no point for me to be tangent to. So my derivative will also be discontinuous there, because as you know, a discontinuous derivative means a non-differentiable function. So this yellow is the derivative graph. After that point my slope is still negative, but it's becoming less and less negative because it's heading back toward 0, because right here you have a slope of 0. After that point it's positive, so you'll notice this is also positive in the positive region, and it's getting very, very steep very quickly, as you can see. So it's essentially exploding toward an undefined slope, or an undefined number, which in this case would be infinity. So you have an infinite slope, and it's becoming less steep slowly, so that number is still positive, but now it's coming down, and it looks like it's starting to flatline. So a derivative would look something like this. And you'll notice this yellow derivative graph is discontinuous because the red graph is non-differentiable at several points. So this basic understanding will help us determine horizontal and vertical tangents in terms of a graph. The key thing to remember is that a horizontal tangent has a slope of 0, and a slope, of course, we think of as a derivative. And a vertical tangent has an undefined slope. So think about what it means to have an undefined answer in terms of just simple arithmetic, and that'll help us figure out how to get the points of vertical tangency. So I have two examples here to illustrate. Here's a typical question. Find all x values where f, the given function, has a horizontal or vertical tangent. And there's no graph, we just have a function here. So the key thing to remember, some of the background that the graph from the previous slide helps us kind of understand, is that a horizontal tangent means the slope of the function there is going to be 0. So the slope we think of as a derivative. So the derivative is going to equal 0, and we've got to find when that's true. A vertical tangent occurs when the slope of the tangent line is undefined, and so we can see that as f prime being undefined. And I'll be a little more explicit about what I mean by that algebraically in a couple moments. So the first thing to do to find the slope of this function, we need to take its derivative. So hopefully you recognize this is a product rule example, because you have two functions here. So I'm going to call this one f and this one g. F prime is 1, and g prime is using the power rule is 2x minus 1. So toss them in the formula there for the product rule, f prime times g plus f g prime. Oops. G prime is 2x minus 1. So product rule. Simplify here, so f prime is equal to x squared minus, x squared minus x minus 11, plus do a little bit of distribution here, so there and there. So let's see, we got 2x squared minus negative 1. So that would be negative 4, so negative 5x plus 2. And further simplifying, f prime of x, I've left off the x earlier, is, let's see, 3x squared. If I combine these, combining these, I have negative 6x, and these would give me minus 9. So there's our derivative function. The question is, when is this thing equal to 0? Because when I can find when it's equal to 0, I know I'll have a 0 slope, because a derivative is a slope. So I'm going to set this thing equal to 0 and then solve for x, because that'll give me the x value locations of any horizontal tangents when the slope, the derivative, is equal to 0, horizontal. So this should be fairly straightforward. Let's see, I can make this a little bit easier on myself by factoring out a 3. So that'd be x squared minus 2x minus 3 equal to 0. Make my butt cheeks here. So x, and let's see, 3 and 1, negative and positive. So when is this equal to 0? Well, that's when each term is equal to 0, so that would be at x equals negative 1, and that would be at x equals 3. So this tells me that if I plug these values into my derivative, I will get 0. And since a derivative describes the slope of a tangent line at a specific point, then these are the locations, the x value locations of my horizontal tangent. So in a sense, we know that there's going to be either a peak or a valley at negative 1, right? So maybe something like this, and then a peak or a valley at 3. So maybe something like that. So you can see that we're building toward how to understand function behavior without having a graph, and we'll eventually get to the point in a couple of weeks of curve sketching, where we can actually basically reconstruct a graph purely from its function and better understand its behavior that way. Vertical tangent would be where the slope is undefined. Well, here's our derivative function here in this mess, this thing right here. Is that thing ever undefined? Am I ever going to get, by plugging a finite number in there, an infinite answer? Am I ever going to have a discontinuity, in a sense, for this function? Well, no, it's a parabola. So I'm never going to have any vertical tangents. And in fact, you can realize that the original function is a polynomial, and polynomials are, they're well behaved. They go up, they go down, they have smooth transitions. Here it happens to be that there are slopes of 0 at negative 1 and 3. Let's take a look at another example, and this will be our last one. Find all x values where, I call this y, let me be a little more precise and call it f of x, where f of x has horizontal vertical tangents. So same question, different problem. So it'll help to make this a little ready for calculus if I rewrite this like so, and take its derivative. So f prime of x, well, that's going to be a little complicated. I'm going to use the product rule once again because I have two functions being multiplied together. F prime is simply 1. G prime is a little complicated, so let me be careful here. So I have 1/2 4 minus x squared, not touching the inside, to the negative 1/2 using the power rule. But since this has its own derivative, I'm going to use the chain rule, and that would be negative 2x. That's the derivative of the inside part there. Well, these can simplify slightly because negative 2x and 1/2 will just give me negative x, and then that would be 4 minus x squared to the negative 1/2. And I can simplify that a bit more by realizing that I can fix this negative exponent and putting it in the bottom. So negative x, and then once I have this on the bottom, it's going to be a positive 1/2, which means the square root of 4 minus x squared. So right there is g prime. So that's sort of the prerequisite to even taking the derivative. So let me give myself a little more room here. So now that I have the parts of my derivative, for the product rule, let me go ahead and actually find the derivative of f prime. So f prime is going to be, it's f prime g, so 1 times just plain old g, which would be the square root of 4 minus x squared, plus f, which is x, times g prime, which as we just found is negative x over the square root of 4 minus x squared. Okay. Now, I did go ahead and simplify the derivative in the red there, but I actually didn't need to, and I apologize for a little bit of a confusion here. So let me pretend for a moment I didn't simplify it. Sorry about that. Didn't think ahead. So let me just leave it right there in red. So let's say that was our g prime for the derivative. And in fact, a lot of you kind of like to just leave your answer as is when you take the derivative, and oftentimes I kind of bug at you and say, oh, well, you should simplify it. But here's an example where it doesn't really need to be. So times negative x, this is g prime, 4 minus x squared to the negative 1/2. Okay. And then if I rewrite this a bit, so putting it in the power rule, product rule, I have 4 minus x squared, oops, to the 1/2 minus, combining these, minus x squared, 4 minus x squared to the negative 1/2. So we saw an example of a problem kind of like this in class last week. So at first blush I might think, well, how am I going to make sense of this derivative, let alone solve it for 0 and all of this? Well, I can factor 4 minus x squared out because it appears in both terms. So f prime is going to further be, once I factor out 4 minus x squared. Well, how many can I factor out? Well, as we saw, you take the lesser of these two exponents, just like you do in general. So I'm going to take out a negative 1/2, leaving me with 4 minus x squared to the first power, because these will combine to give me positive 1/2, minus, I'm taking all of this out when I factor it out, so just minus x squared. So the 1 doesn't here really do anything. These will simplify. So on top I have 4 minus 2x squared if I simplify those. And on bottom, because I'm going to go ahead and put this on the bottom to fix the exponent, I have 4 minus x squared. So after all that, we finally have our derivative. 4 minus 2x squared over 4 minus x squared. So we're now ready to answer the question, where does it have a horizontal tangent and where does it have a vertical tangent? So you'll notice that this derivative, in contrast to the previous example, is a fraction, right? So a horizontal tangent, we kind of saw in the last example, so it's not too bad. It's when the slope is equal to 0, so when it's this thing is equal to 0. Now it's important to realize that the top and the bottom could, in a sense, both be 0, or rather, each could be 0. So which of these two numbers that I'm going to write is actually equal to 0? Is it 0 divided by a number, or is it some number divided by 0? Well, as we know, you can't divide by 0 and get a defined result, so we need 0 divided by some number. In other words, to find a horizontal tangent, we need the top, the numerator, to equal 0. So I'm going to set this thing equal to 0 to find my horizontal tangent. By contrast, when you divide by 0, you're essentially getting an undefined answer. In fact, when you try to divide by 0 in a calculator, you get undefined. So to find the vertical tangents, which is an undefined slope, slope is derivative, you set the denominator of the derivative equal to 0, and there is where you would find any vertical tangents. So numerator would give you horizontal because it's 0 divided by something. Denominator will find you the location of any vertical tangents. Now you want to be careful because you cannot divide 0 by 0. As you know, it's an indeterminate form. So just because you get 0 on the top, make sure it doesn't also give you 0 on the bottom, because it's 0 divided by a number. And I know 0 is a number, but in general I mean some quantity. So all that said, let's go ahead and find the horizontal tangent. So that's going to be 4 minus 2x squared is equal to 0. Well, that's 4 is equal to 2. Actually, let me do this the proper way. I'm going to factor out a 2. So that would give me 4 minus, or rather 2 minus x squared. 2 minus x squared is equal to 0, which is going to be 2 minus x squared is equal to 0, so 2 is equal to x squared. So x is equal to plus or minus the square root of 2. So there are the locations of my horizontal tangents, plus or minus the square root of 2. And I'm going to do the verticals here in red, to going to give a contrast. And for vertical tangents, I'm going to set the denominator equal to 0, so that's going to be the square root of 4 minus x squared equal to 0. Well, the square root of 0 is 0, so really if I have a 0 on the inside here, that's really what I'm interested in, because the square root of a 0 will give me 0. So that's going to factor, into 2 plus x, 2 minus x, and then that's going to give me the answer of x equals plus or minus 2. So my vertical tangents occur at plus or minus 2. My horizontal tangents occur at plus or minus the square root of 2. So if you actually graph this function, you'll notice it's quite funky looking. You have some peaks, you have some valleys, and some other interesting behavior there, and this tells us basically where the slope is 0 and where the slope is undefined. Alrighty, see you in class.